Hey everybody, what's going on? Up until now we've been talking about finding the area underneath the curve, but we've been approximating it using either trapezoids or rectangles or counting squares, any approximation that we could use. In order to move beyond just approximating and finding the exact value of the area under the curve, we've got to talk about something called an antiderivative. There's no really good way to talk about an antiderivative other than just to tell you what the definition is and then show you some examples because it makes way more sense in the process of it. So read with me here. A function, and we call it capital F of x, that's just notation that has been around forever. I don't know why they don't call it G or a different letter, but they use capital F of x, and they say that capital F of x is an antiderivative of another function, little f of x, if and only if f of x, the little guy, is the derivative of capital F of x. Okay, so that sounds really exciting, but let's take a look at it. So take a look at the two functions. We've got little f of x equals 5x to the fourth. We've got capital F of x equals x to the fifth. We say that capital F is an antiderivative of little f, because if you take the derivative of the capital letter, you end up with the exact same function as the little one. So as soon as you establish that relationship and you get that the derivative of capital F of x is the exact same function as this little f of x, then we say that capital F is an antiderivative of f. Okay? I want you to write down in your notebook what another antiderivative of f of x is, little f of x. So if you think about this function right here, all you have to do is determine what other function can you think of that when you take the derivative, you will get 5x to the fourth. Okay, so that's your job. In general, we say that capital F of x is an antiderivative of f of x. Then capital F of x plus c would also be. We call c a constant of integration. So there's two types of solutions we can come up with. One of them is a general solution where we just tack on a plus c for finding an antiderivative. And then we've got something called a particular solution where we've got more information that is given to us and we're able to find an antiderivative that will satisfy certain conditions. Okay? Typically, that condition is called an initial condition, but we'll get to that in just a little bit. Now, up until now, we've always had numeric bounds on our integral, and that was finding an exact area under a curve given a starting x value and an ending x value. But this time, we're going to be solving indefinite integrals. And I'm just going to wipe right over that. Let's try that again. We're going to be solving indefinite integrals. And all that means is an indefinite integral is asking you to find an antiderivative of an integrand. And if you don't have bounds of integration, it's asking you to find a general solution, which means you're going to just tack on a plus c. Okay? The operations of finding derivatives and antiderivatives are inverses of one another. So all that time and effort you spent studying your derivative rules first semester is really going to pay off now. And if you're thinking, oh crud, I didn't know them very well first semester, this process is still going to help you with that because you need to know them forwards and backwards. Okay, so let's go through all the rules of finding antiderivatives. First of all, we've got our derivatives on the left-hand side, and then we'll talk about the antiderivatives on the right. So if you are taking a derivative of a function times a constant, we had said that there's a constant multiple rule. And that rule says that you could just pull out the constant to the front and then just do the derivative of the function afterwards. Okay, so the same rule applies when you do an antiderivative. If you have a constant that's being multiplied to your integrand, then you can just pull that constant out to the front and then use your antiderivative rules to come up with the answer for your indefinite integral. Okay? Likewise, with our sum and difference rule for our derivatives, we've got a sum and difference rule for antiderivatives. if you've got two functions, f of x and g of x, you can break them up depending on if it's a plus or a minus, and just do each antiderivative or indefinite integral separately. Now the trick here is you have to remember that you've got a dx for both of them. Because remember, dx is telling us what variable we're integrating with respect to. Okay? So those are the constant multiple and the sum and difference rule. Okay? If you have any questions from this first page, make sure you circle them, write them down in the margin, and we'll get to it tomorrow. Okay, here's where we're going to get into some more specific rules. And the derivative rules are on the left, and we're going to talk about the antiderivatives on the right. So on the left-hand side, if you were to take the derivative of the sine of u with respect to x, you would just get the cosine of u times du dx. So that's that chain rule kind of involved. Here on the antiderivative side, we're going to be taking the antiderivative of the cosine of u with respect to u. So in this case, u is actually our variable. So all you have to do is ask yourself, what function, when you take the derivative, will give you the cosine of an angle or a cosine of a variable? And in this case, it is the sine. And let me put my pen on. There we go. Okay, it's the sine of the variable u. Now the trick here is remembering, if you don't see numbers on the bounds, you're not actually finding an area under a curve. You're finding an antiderivative. So any constant added onto that function will give you the derivative of the cosine of u. Okay, so you have to include the plus c. And let's take a look at our next one. We've got the derivative of the cosine of u. The derivative of the cosine of u with respect to x is going to be the negative sine of u times du dx. Okay, so that was our derivative for cosine of an angle becomes negative sine of the angle times the derivative. Well, if you look over at the antiderivative side, the antiderivative of the sine, okay, so what function when you take the derivative gives you the sine? Well, it's tempting just to say the cosine. And if you say the cosine, think about it. Take the derivative of the cosine of u and you'll get a negative. So that's not quite right. We have to put on a little negative guy there. Okay, so everybody's heads are spinning, right? So the antiderivative of the sine of u is actually the negative cosine of u plus c. Again, the better you know your derivative rules, the easier your antiderivative rules are going to be. All right, I'm going to challenge you right now to press pause and try the next 4 antiderivatives on your own. Again, you're just asking yourself, what function, when you take the derivative, will give you the integrand? Okay, so press pause. Do it now! Do it. Okay, press pause. Okay, let's see how you did. The antiderivative of the secant squared of u is just the tangent of u plus c. If you remembered the plus c, yay! If you forgot it, don't do it again. So quick, go put your plus c's in if you forgot them. All right, so the antiderivative of the cosecant of u cotangent of u is actually the negative cosecant of u plus c. The antiderivative of secant u tangent u du is going to be the secant of u. And the antiderivative of the cosecant squared of u du is going to be the negative cotangent of u plus c. Oops, I forgot my plus c's. Ah, there we go. Okay, so again, I don't think it's anything you need to memorize. As long as you know your derivative rules, you can figure out the antiderivatives. Okay, let's go ahead and take a look at our power rules now. And we're going to move this guy up a little bit. All right, so our power rules. For derivatives, we said that if you have a variable raised to a constant, then you could take the derivative just by bringing down the constant to the front, leave the variable alone, drop the power by 1, and then multiply by the derivative of the variable. And in this case, we're going to notice that u is our variable here, and n is the constant. So an antiderivative works in reverse. Okay, so the first thing that you're going to do is add 1 to your power. So that says u to the n plus 1. And then you're going to divide by the new power. And tack on your c. Okay, so before we would deal with the power first, bring it to the front, and drop the power by 1. Now we're going to add 1 to the power and divide by the new power. Okay, so I've got a couple of antiderivative practice problems right here, and if you'd like to try them on your own first, you are absolutely more than welcome to, except for number 3. I wouldn't recommend doing number 3 on your own. But number 1, change out of the radical and change it to an exponent, and use your antiderivative rules that we just talked about. If you'd like a little bit of guidance and you don't want to try it alone, that's okay too. But either way, let's go ahead and do number 1. Okay. If you would like to rewrite this as 3x to the 1/2 dx, that would be my first step. Just like before, I'm going to use the constant multiple rule that we used for derivatives. I'm going to use the same thing with antiderivatives, and you'll get used to not showing this step that I'm writing right now. But at the beginning, I like to show it just to show you all the antiderivative rules as we'd use them. Okay, so the first thing I do is I pull out the constant, and now I'm going to use that power rule. And the power rule says you're going to add 1 to the power, so that becomes x to the 3/2. Let's see if I can make that look like a 3. There we go. X to the 3/2, and then you're going to divide by the new power. Now, another thing you'll get used to is, especially if you have fractional exponents, dividing by the power is going to be the same as multiplying by the reciprocal. So this is going to give us 3 times 2/3 x to the 3/2 plus c. Okay, so the 3's are going to cancel, and you're going to be left with 2x to the 3/2 plus c. Now, the coolest thing about antiderivatives, I know I used cool and antiderivative all in the same sense. Do you believe it? But the cool thing about this is if you're really good with derivatives, you can always check your answers. And when you take the derivative of your antiderivative, you should be left with the integrand. So I'm going to do the check in red, and I'm going to try to squeeze it in because I didn't leave myself enough room, but that's okay. The check for this is if you take the derivative of 2x to the 3/2 plus c, you want to ask yourself, do you get back to the integrand? And the integrand was 3x to the 1/2. Okay, well, think about it. When you apply the power rule, you would have 2 times, you would bring the 3/2 down to the front times x to the 1/2. The 3/2, the 2's would cancel, and you'd have 3x to the 1/2. And that's exactly what we had in as our integrand. So yay, it works. Okay. If you haven't tried number 2 on your own, I want you to try number 2 right now on your own and then come right back. All right, how'd you do? Let's see. First thing is you could split this up into multiple integrals, indefinite integrals, and say that this is the integral of 3x squared dx plus the integral of 2x to the 4th dx, etc., etc. Okay, is that really necessary to do? No, it's not really necessary. You can leave it if you want to and finish off the rest of it, but for the sake of saving space and time, I'm just going to deal with each one separately. So the first thing is you're going to have the 3. Wow, that's a terrible 3, isn't it, everybody? Woo, good times. Okay, you're going to have the 3, and you would have x squared. Now, in order to deal with that, you're going to raise the power by 1 and divide by the new power. Okay, so that would be the antiderivative of 3x squared. Then you're going to deal with the 2x to the 4th. The 2 is a constant, so leave it out. Now x to the 4th, you're going to raise the power by 1 and divide by the new power. 1/2 x cubed, raise the power by 1, divide by the new power. 7 x raise the power by 1, divide by the new power. And I'm running out of room, but this is going to continue on. Now 1 plus 1. Okay? If you want to think about it as x to the 0, this guy right here is really 1x to the 0. You can think about it like that, or you could just ask yourself the simple question. What function, when you take the derivative, gives you 1? And the answer is just x. Okay? So that whole piece is our indefinite integral, aka antiderivative, and I'm leaving a little bit of space because there's one more thing you have to do. You have to add c, okay, because the derivative of a constant goes away. All right, everybody, we've got one more problem to do on this page and then one short one on the next page. Hang with me. Take a break if you need to, but come on back. Okay, again, in the interest of saving a little bit of space, I don't want to delete that guy. Hang on one second. I want to use my little eraser here. Okie dokie, I've cleaned up a little bit of room here. Now, when you have one denominator in an integrand and two numerators split up by addition or subtraction, you can use your properties of fractions to help you simplify this thing before you ever do an antiderivative. And that's very similar to the techniques that we used when we were doing derivatives. So the first thing I'm going to do is I'm going to rewrite the integrand, 5x cubed. Instead of writing 1 over x, I'm going to write x to the negative first. And instead of writing 2 rad x, I'm going to write 2x to the 1/2. Now remember, the 1/2 power is only being applied to the base of the x. And this is dx, meaning with respect to x. Now you can break this integrand up and write two separate indefinite integrals. Now, as beautiful as that is, there's actually a purpose to it. And that is that we can use our properties of exponents now. Again, I haven't done any calculus, but we can use our properties of exponents to help us clean this up a little bit. So with that first indefinite integral, I'm going to pull out the 5/2 to the front because that's a constant multiple. And x to the third over x to the 1/2. Well, what I'm going to do is I'm going to get common denominator so that I can apply my properties of exponents. X to the third is the same as 6/2, right? Getting common denominators. And then we know that we can change this. Instead of having x to the 6/2 over x to the 1/2, you can subtract it and just make it x to the 5/2. Okay, so that's that first integrand. I want you to use the same technique, clean up the second integrand, so hit pause right now and come on back and check your answer. All right, how'd you do? Change the -1 power into a -2 over 2. Technically, there's a 1 in the numerator as a coefficient in front of the x, so I pulled that out to the front along with the 2 from the denominator. So right, there was a 1 here, so I pulled the 1/2 out to the front. And then a -2 over 2 over a 1/2 power makes a -3/2. Okay, so again, it's typically not the calculus that messes us up at this point. It's usually the algebra skills. So we're going to apply our properties, our power property for antiderivatives to come up with the correct antiderivative. So for the first integrand, we had the 5/2 out in front. If you raise the exponent by 1, add 1 to the exponent, it's going to be 5/2 plus 2/2, so that's 7/2. And then when you divide by 7/2, our new power, you're actually multiplying by 2/7. So I'm going to squeeze that into the front. Okay, and the reason that's helpful is because the 2's from both of them are going to cancel. Okay, now technically there's a plus c here, but I'm going to just lump it in with the second integrand's the second antiderivatives plus c, because a constant plus another constant is just another constant. So if you have questions about that, we can clarify in class tomorrow. So we have minus 1/2. We've got x to the negative 3/2. When you add 1 to that power, you'll have a negative 1/2. When you divide that by negative 1/2, you're technically multiplying by a negative 2/1. And here that cancels with that guy. Negative times a negative is a positive. And, whoa, redo. I just lost that whole piece and I don't know where it went to. So I hope you wrote that down. Good times. Okay, so our final antiderivative is going to be 5/7 x to the 7/2 plus x to the negative 1/2 plus c. Okay, and again, you can double check and see if you got the correct antiderivative by taking the derivative and seeing if you end up back at the integral, or I'm sorry, at the integrand. Okay, one more problem. Bear with me, one more. All right, well, congratulations. You've made it to the last page of the note, so I'm going to try to speed through this, but also be very clear about it. All right, number 4 says, given that g prime of t equals 1 plus secant t tangent of t, and we know that g of pi equals 2, we are asking, being asked to find the original g of t function. Okay, so we're told the derivative of g. We want to find what g is. So that means we're going to utilize an antiderivative. Okay, so what function, when you take the derivative, gives you 1 plus secant t tangent t? And the answer to that, what function gives you the derivative of 1? Well, that would be t. What function gives you the derivative of secant t tangent t? And that would just be secant t. And we would have a plus c in there. Okay, if you take the derivative of g of t, you will end up with g prime of t, which was given to us. Okay, so there's our function. Well, we're going to go a step further. This little guy right here, g of pi equals 2, that guy right there is called an initial condition. It is used to help us determine the c value. Okay, so it says find g of t. Well, g of t, we can solve for c by plugging in t is pi and g of pi is 2. So this is going to be a 2 here. And everywhere you see a t, put a pi instead. Oh, I hear the whimpering already. We have to take the secant of pi. Oh, no. All right, hang in there, everybody. Remember, secant is 1 divided by the cosine. So think about your unit circle or think about a cosine function. What is the cosine of pi? And the answer to that, cosine of pi, come on, cosine of pi, is negative 1. Good. So you can put a plus negative 1 or you could put minus 1 plus c. Now the whole purpose here is to solve for c. If you add the 1 over to the other side, 2 and the 1 makes the 3, and you would subtract pi to the other side. So you have 3 minus pi is your c value. So your final answer, and I'm going to change colors here to show you that this would be our final answer, our g of t function equals t plus the secant of t, and then instead of putting plus c, you're going to substitute your c value of 3 minus pi. This function, when you take the derivative of it, will give you g prime, and it will also satisfy the condition that g of pi equals 2. Okay? So that is our lovely long lesson, and I hope you guys have a good night, and I'll see you tomorrow. Bye!